Hello all. So, section 4.9 is all about what is called the antiderivative. And if you've done any studying about calculus at all in terms of like where we're going this whole quarter, you'll know that we're going to be talking about integral calculus. The idea of an integral is, in essence, we're undoing, or we're doing the opposite or the inverse function of a derivative. So we'll spend most of our time on this whole chapter, or this whole not chapter, this whole the quarter is we'll be talking about two things basically. How do you find this particular antiderivative that you've just come across? Because some of them are really easy and some of them are really hard. Ones that you're going to spend a lot of time going, well, if it looks like this, I need to use this kind of a situation. If it looks like this, I need to do this. Others you're going to have to memorize. And so today we're going to do some very basic ones. And then after we do that, we're going to spend quite a bit of time talking about, okay, well, how do you apply these things? What are they good for? Okay. So today we're going to start with some very straightforward ones. We'll do it kind of like this. We will say things like, you'll either say like, find the antiderivative. Well, that's one way to write it. And so one way to say that, okay, here it is. And so if the antiderivative, and we usually write it either as y prime, as you remember, or we might write it as f prime of x, or we might write it as dy dx, or about 1,000 other particular scenarios. So let's just say I have it as y prime equals 3x plus 2. Okay. Well, now, who is this the derivative? How in the devil did you get here? Well, you might recall that in the first course in calculus, you took a derivative. You said, well, all right, I'm going to bring this fella down and multiply it. So it's going to be 2 times x. And you're going to subtract 1 off the exponent. Okay? And then, of course, same thing here. 3 times 1 is 3. And then x to the 0, of course, is 1. And then, of course, the derivative of a constant just goes away. So when I do the opposite of that today, we're going to say, well, this is going to be 3x to the second power. In other words, we're going to add 1 to the exponent. And then instead of multiplying, we're going to divide by that power. And we do the same thing here. It's going to be 2. This is going to be x to the first power divided by 1. I'm going to go ahead and show that. And then, of course, we're just going to put a big constant on the end of it. Now, we don't know what that constant is. We can't really know what that constant is. We just know when you take a derivative, it goes away. Therefore, when you take the antiderivative, a constant has to come back. So our final answer is going to be, and you can write it any number of ways, 3/2 if you're a fraction person, 1.5 if you're fractophobic, and then just 2x, you look like an idiot putting a 1 up there, and then plus c. Okay? So we'll do a bunch of these. I'm going to do several examples of this, so just, don't get excited. They're not very difficult. Sometimes you'll already have a fraction. Oh, no. No big deal. Apparently I have a 3 thing going on today. It's not weird. No, it's totally normal. Sure, let's do that. So then f of x would be equal to, well, of course, now it's going to be 3/7 x to the 9th power divided by 9. We'll worry about that in a minute. Plus 3x to the 5th divided by 5 minus 2/5 x to the 3rd all over 3 minus 2x plus a constant. And so if you clean that up a little bit, that's really 3/7 divided by 9 is the same as timesing by 1/9. And of course this is just 3/5. I'm going to leave it alone if that's all right with you. 2/5 times 1/3. And these cancel just like Mrs. Stockton told us back in 6th grade. That woman made an impact on me. She taught me how to do fractions, by George. She taught me how to yell at children as a teacher, to scare the bejesus out of them. But she did a pretty good job of teaching, so that was good. There's my equation. Yay! Now, of course, you've done it right if you took the derivative and it went back to where you started from. So let's check that out. Suppose I take f prime of x. Well, that's going to be 9/21 x to the 8th plus 3, well, 3/5 times 5 is 3, x to the fourth, minus 6/15, whatever that is, x to the second, minus 2, and of course the derivative of constant goes away. Of course this simplifies to 3/7, so that's cool. And x 2/15 is really just what? It's 2/5, I guess, isn't it? There you go. And voila, there's our equation. In other words, it's just a quick way to check it is just to do the power rule, take the derivative again. It's not very tough to do. Now somebody might say, well, Jay, is there another way to write that? Well, of course there is. So this thing right here is what's called the integral sign. And I show it to you now, because in this section they don't show it to you, but later on, they may introduce it one time. But later on, this is how we'll always do it. So if you see this is what they're saying, is to take the antiderivative. There's a kid I had in class last year. He would be just crying right now because, why did you do it in the wrong order, Mr. Groom? Just to see if you're paying attention, that's why. And so the antiderivative would be 3x to the third over 3. Plus, some of you are realizing that that could have been done in a simpler step. The way I did that, really just been x cubed. That's all it's going to be. And if you see that, knock yourself out. I don't care. It's one of those things that over time you'll get good at. And so you won't have to fool with it. Oops, not plus 1, dummy. Plus c. There you go. So that's x cubed plus 6/5 x to the fifth. And of course, this is going to be 3/5 times 1/8. Which is 3 over 40, x to the 8 plus x plus the constant. Don't forget your constant, because it's technically not the antiderivative unless there's a constant on the end of it. Okay? Someone might say, well, Jay, what if it was one of these guys, 3x cubed minus 2x plus the sine of x? That's a great question. What if it was? Good idea. So, if that were true, it would be 3x to the fourth over 4, of course, minus, this one's really going to be just x squared, but let me just show you. It's going to be 2x squared over 2, because this is obviously the derivative of x squared. You probably knew that going into that. Who is this guy the derivative of? Where did you get sine from? Well, I feel like the derivative of sine is negative, I feel like sine is the derivative of negative cosine of x. In other words, if you take the derivative of negative cosine, you will get sine. Okay? In other words, sine is the derivative of minus cosine. Now, this will not be introduced this section. Okay? It's not. But it's one of those ones that you should be like, oh, duh, that makes sense. I remember that guy. I remember doing those, taking derivatives, so it's not hard to undo the derivatives. Another one that might come to your attention is this. If you want to find the antiderivative of this plus this, maybe I put a 2 in front of that while we're at it. I don't know, plus cosine of x minus 7 or whatever. Well, who is this the derivative of? Wait, e to the x is his own derivative, so he's probably his own integral too. In other words, yes. If you take the derivative of this, you get right to there. That's right. Where did this guy come from? Well, he came from 3x to the fifth over 5. Minus 3x squared over 2. Who is that the derivative of? I feel like that's the derivative of sine. And I really can't reduce any of that anymore, so I'm just going to leave that one alone. Nice? I think so. Alright, now there is one other kind that they tell you what's called an initial value problem. And the only difference between this one and the last one is they will tell you that, hey, look, f of 0 happens to be, let's say, 6. Or it could be f of 1 or f of 19, or it doesn't make any difference. In other words, what they're saying is, here's an x, here's a y, find that constant. So if you had this equation here, and I said find the antiderivative, you would say, well, that's x cubed plus 7x cubed over 3 minus 2x plus a constant. In other words, if this were f prime of x, this would be f of x. Does that make sense? Now, interestingly enough, I want to know what c is. Well, that's a good question. Well, I know that f of 0 is equal to 6. And what? Well, that means that all these x's are 0. So 0 plus 0 minus 0 plus c. In other words, c has to equal 6. So my final answer would be this guy right here. Okay, it is that easy. If it hadn't been equal to that, if it had been f of 1 equals 2, then it would have been a slightly different problem, because then I would have had to do this. All right, we'll put 1 in everywhere. And so it would have been 3 plus 7 minus 2. Oops, where'd I go? 3. No, not 3. Let me try again. We're putting a 1 into here. It's going to give you 1 plus 7 thirds minus 2 plus a constant. And so it seems like over here this is it's negative 1. This is 1 and that's 2 1/3, isn't it? Well, it's 2 1/3, isn't it? It's 2 1/3. Minus that is 1/3, so 1 1/3 equals 2. So that means c is equal to 2/3. Yay! And that would be how you do it with that one. It's not a big deal, not a big difference at all. Just be aware that sometimes they'll do f of 1 or f of 2 or f of 19. There really is no rhyme or reason what number they pick out of there. We do like f of 0 frequently. We like it frequently, especially later on when you get to a class called Differential Equations, because that's typically what we're interested in, what happened when time equaled 0. Okay. Now, somebody might well ask, well, what would the antiderivative be, Jay, if you had 3x squared plus 6x? Okay, all good so far. Plus sine of x, and so you're not upset yet. Plus, and then someone throws this weird one at you. The ln of 3x minus 7. Hey, yes, I can do this one right now. You with me? Totally. Yes, I can do this one right now. Not a problem. Sure, this one's easy. But you see, this one here I can't do yet. This is one of the ones that later on we're going to have to find out when it looks like this, where there's a function in a function, I'm going to have to use other techniques. In other words, there's a reason why we do it in the order we do it. Maybe you run into this one. You say, all right, I want to antiderivatate, or take the antiderivative of this guy. Well, good luck with that, because that's a bugger, because it's a product right there. And because it's a product, I have to jump through a bunch of hoops, and it's a different story. If someone told you to take the derivative of that, well, yeah, of course you use the product rule. It's the same thing, though. When we did the product rule, you said, well, look, if there was a multiplication property here, then I'm going to have to use the product rule to take the derivative. Integrals are similar in that regard. In that, if it looks a certain way, this is the technique we'll use. If it looks this way, this is the technique I'm going to use. Again, some of them are going to be ones that you're just going to have to memorize. For instance, what is the antiderivative of minus sine? Where did it come from? It came from cosine, of course. Okay? And again, that's one that you've memorized over time. Here's one where if I said, hey, f prime of x is equal to e to the 2x, one might be able to figure this out before we actually teach it to you. One might actually be able to figure that one out. And it kind of makes sense, because if you think about it, if you take the derivative of e to the 2x, what do you get? Well, the derivative of that, you may recall, is, well, it's e to the 2x times the derivative of 2x, which is 2. So in other words, it would be 2 e to the 2x. Well, in other words, this doesn't derivatate to that. It would have an extra 2 in front of it. So in order to account for that, instead of multiplying by this 2, I'm going to divide out by that 2. And so you could probably talk yourself into getting that one right, but there's going to be a lot of other problems where we jump through a lot of hoops in this situation. So again, kind of picture this. The way this whole quarter is going to work, we're going to have a little bit of how come. Why do we do this? How come? A little bit of, I should say a lot of how to, and then a little bit of application. Okay, it's going to be kind of how it comes out for us. Okay, How comes? What do we? How do we go about them? What does it mean? We're going to do some of that. Today, obviously, we just did a little bit of how-to. The next couple of sections are going to be about how comes. Then we're going to move on back into, we're going to do a whole bunch of how-tos. And then toward the end, we're going to do the application piece of it. Okay. So pretty straightforward, I think, for the most part. There's not a whole lot of work to show. The kind of work that you'll be showing in this section will be things like this. Hey, it's 7x to the third divided by 3. That's the kind of work that you're going to show. If it's an initial value problem, this is the amount of work that I'd expect you to show. Okay, and we'll call that a wrap.